Hey everyone, I'm Lu. So I'm going to share the topic about how to maximize our GPU utilization for model training. I see it's that same introduction as James have introduced. So first, I will briefly introduce what is the Elastic Data Platform. You can consider it as one is like a high performance data access, and the other hand is able to connect to different storage systems. So basically, it brings the data of different storage systems closer to different frameworks, like the big data frameworks like Spark, Presto, and also the AI frameworks like PyTorch and TensorFlow. So it brings the data closer and provide high performance data access. So for the functionality side, it have different aspects. The several main aspect is that it provides distributed caching capability, it provides the global data access, and some data management, including like some data migration. So on this session, we will briefly talk about some of the high-level design of implementation of this Elastic Data Platform. So this for first comes with like actually the problem of like from many of the model training jobs, we actually found that data locality become the issue, especially when those training job they need to get a really huge data set in their storage system ready in their training system. And also like in these cases, like many of the training workloads, they are running in Kubernetes cluster, which is the aggregated from their cloud storage systems. Their storage system may be like cloud storage system, like either S3, Azure, Blob Storage, or the Google Cloud Storage. Or is like on-prem data storage, like HDFS or Ceph. And how to make those huge data set in their storage system ready for their training is become a problem of that. And so consider every time you go through the whole network to get the data ready, it's like the latency may be really low and the throughput latency may be really high and the throughput may be really low. And this will directly result in a low GPU utilization rate. And also for many training jobs, they use the same data set again and again. So every time we need to fetch the whole data set from the storage system to the training jobs, it kind of like have a really high storage cost for data transfer fee, because every data that transfer from the storage system to the training job, it costs money, like from all the cloud vendors. And there are multiple solutions to solve this problem. So first part is that the users, just as I mentioned before, you can always fetch the entire data set from remote storage on the fly. But the repeated fetching the data set from the remote storage is because it may like lowering the data loading performance and also lowering the GPU utilization rate. Or you can copy the data set from remote to local before training. However, this approach really requires that the whole data set can be fit in your local disk, which may not be the case in many of the training workloads. The training workloads, the GPU clusters, they may not have this available, or their disks have a limited capability. And the other way is to have a local cache layer for data reuse. So we still need to fetch a data set from the remote storage, but we can cache the most hot data in the local so that we can reuse them in the next round. However, like in many of the training workloads, we use the same data set from epoch to epoch. However, this is from the cluster level. But if you consider it from the single node level, we may not reuse the full data set. There will be data shuffling between each epoch, so that the data reuse rate probably like only 10% or even less. So only limited benefit can be provided by this local cache layer. So there is also some distributed caching approaches. Basically, like we can cache the data in a distributed system, which can store much more cache data compared to the local cache. And this is one of the ways that many caching systems do before. So we have the master and worker architecture. So master basically is the brain of the whole cluster, but it also becomes the single point of failure. It provides you all the data management functionality, but it also are on the critical path of each read or write request. So basically, if the master done, the whole cluster are not able to serve any request, and will result in your training job to actually fail. And on the other hand, this master worker architecture made the master become the performance bottleneck of the overall performance. So consider like each of the read requests, you need to talk to master to say that, hey, I want to read this file. And then you need to talk to worker to actually get that file. Then asking the master you want to get a file or asking the location of that file becomes the performance bottleneck. In the AI training job, the job is easily can exceed like tens of thousands queries per second. So if every time it go to the master, then master will definitely become the bottleneck. Even a huge machine are not able to serve like tens or hundreds of QPS. So another way that we are doing now is using consistent hashing to cache both data and metadata on workers. So basically, we remove the single point of failure and we remove the performance bottleneck. Now client directly knows that which worker that she should ask like data and metadata to, and then directly connect with that worker. So but we also keep the data management system. Basically, we still have the many features like how can we migrate data from one star system to another, and etc. We still have a visibility of like what is in the cluster. However, there's some new challenges happening. The first one, because like client directly connect to worker to catching data and fetch the cache data, then there's a direct problem that what if the worker load is imbalanced? Maybe one worker, they store more data and that worker also serve more clients, then that worker will be super busy and while others being idle. And in this case, the overall performance may be hurted and it will also lead to outages. And way to solve this is that it's called the affinity caching solution. So we optimize that with affinity caching. So users, they can configure how many replicas they want to cache. They want to cache 1 or 3, etc. And we will use the consistent hashing to determine the first choice node for caching. So like we will first go to this first choice node to see that, hey, do you have the data and are you able to serve me? And if they are not, you just go to another node, another waiter and see that whether they can serve you. And then if not, you go to the serve one. So this is basically the logic. If all nodes are super busy, then we will always fall back to the cloud storage and we will directly ask the cloud storage to provide the data set. And so when you're reading from the caching system, it just like found the first node and then get the data and then found the second node if the first node fell. But usually in most of the cases, the first node should be able to serve your request. And this way is to prevent the nodes become super busy and prevent the imbalance in maybe like less than 10% scenarios. And now we are going to share about how we actually maximize GPU utilization at Microsoft, Shopee, Zhihu, and many other our users. This is a typical large language model pipeline that we found that many of our users, they don't have a single cloud. They actually have multiple cloud to prevent the cloud vendor locking. So, and they also have different training and serving jobs and different clouds. And really depends on the price of their GPU machines and the resources, etc. So, but it results in on the infra side that they have different training jobs, different serving jobs that are not co-located together. And so that we found there's several problems in this architecture. So on the left side, we have a model training job that running PyTorch, and then it need to fetch the data from the object storage. And in this way, the training job need to repeatedly fetching the same data set from the storage system at a really high concurrent request. And it will have two consequences. Like the first one is that because the training job need to fetch data remotely, If the data loading maybe takes more time than expected, and it may become the training job bottleneck, it will result in low GPU utilization rate. On the other hand, the storage system may have a huge pressure. So there are two ways that they handle that. For many of the cloud storage, they basically give you a request rate limit. If you exceed that request rate limit, basically you have errors when you're reading the data. And depends on whether your training jobs handle those errors well, it may actually affect your training job stability. On the other hand, for some on-prem storage system, if you put a highly concurrent workloads onto your storage system, it may put your storage system at risk. And so there are many times that when we talk to some of our users, their data team will actually yell at their training team saying that you guys affect our stability and you put us at risk. And can you guys stop doing that? Because for the on-prem storage, they need to make sure their data is safe. They need to make sure their existing write workload and their existing other long-running read workload function as normal. So if there was a circumstances that the training jobs takes all their capability of serving requests, then they cannot serve other requests well, and it may result in a much severe circumstances. On the other hand, there are also the serving cluster. The serving cluster, their request is to deploy the model quickly to all the serving nodes. So the quicker that we deploy the models, the quicker we are able to see the actual business impacts. And if the model does not work as expected, we also need to quickly roll back to the previous version. So have a way to quickly deploy the new model and quickly revert to the older models critical for the inference cluster. And their solution is basically they put a caching layer between the training jobs, serving jobs, and also the storage systems. So on the training job side, they can use this caching system to fetch the data from remote storage, caching it locally, and provide the data set to their training job so that the data set only be need to fetch from storage once, and following requests will be served by Alacio. And also on the other hand, because the data is much closer to the training jobs, it can provide much lower latency and much higher throughput. And basically, it can improve the overall GPU utilization rate. And on the other hand, on the serving cluster side, we can help fetch the model into Alacio as a model storage. Then the models only been loaded from Alacio to all the training nodes. And this can provide much faster model loading compared to loading always across the network to the remote storage system. Basically, from the business side, it can achieve 2 to 4 times faster time to market. On the technical benefit side, it can increase the GPU utilization rate. And we do have several benchmarks that showing how we can achieve those performance benefits using different compute frameworks. The first benchmark is using PyTorch and Alacio. We launch Alacio via Kubernetes. Basically, we provide caching for the training data. All the training jobs and the Alacio system is launched directly in the Kubernetes cluster, and they are either co-located or near each other. And we use some popular deep learning algorithms and deep learning data sets like the ResNet and ImageNet. And we have some visualization dashboard. A pretty standard benchmark that we did. Okay, so basically this is the script that we do the AI and machine learning training. It's pretty standard, just similar to how you guys did the ResNet, in ResNet 50 on the ImageNet. That's it. And so yeah, everything is pretty standard. And now we start running the benchmark. And one critical point here is the data preparation. So basically, Alacio turns your storage data set into a local path to be consumed by the training jobs. So for here, you can see the data path is just a local path under NT Alacio fields. And we provide this local data path to the storage to the training jobs so that it can consume the data from this local path. And Alacio on the backend help fetch the dataset from the remote storage, catching it in a distributed system, and then provide high performance data access to all the training workloads. And we do the typical like touch data loader and the ResNet 50 training. Everything is just as what the industrial do, and it's nothing surprise. And then we finish the training, and we can look at the TensorBoard. So for the TensorBoard, there are two key points here. And the first one is the data loader rate. We can see the data loader rate is only like 0.54%, and it directly results in a high GPU utilization rate of more than 90%. And there are also some dashboards that showing that how many of the operations is hit against Alacio is hash hit, and how many of them are actually go to the remote storage, etc. So we basically compare this benchmark from using data cache in Alacio compared to the same region S3. So when the training directly load the data from same region S3, more than 80% of the total time is spent in data loader, and directly result in a really low GPU utilization rate, which is less than 20%. And when you guys see similar like graph like this, that's the time that you may consider adding a caching system. It depends on how big is your data set. You may consider like using a distributed caching system or another way of a shared volume. And after using Alacio, training with Alacio reduced the data loader rate from 82% to 1%, and it increased the GPU utilization rate from 17% to 93%. Okay, that's for the PyTorch part. We also have some benchmark about the rate. For some of you guys that may not be familiar with rate, so rate is basically a distributed scheduler. It helps you to schedule your training job together with some preparation steps. So basically, you can schedule your data loading, data preprocessing, and training jobs together to fully utilize your GPU and CPU resources. And Alacio's position in the AI ecosystem is that like consider Ray as a unified compute, a machine learning pipeline orchestration. It wraps around the compute framework like PyTorch and TensorFlow. And between PyTorch and TensorFlow, they need to fetch the data from remote storage. And Alacio can act as a high-performance data access layer between the compute framework and the storage systems. And we do some of the benchmark using the Ray nightly test, which is published in their public GitHub repo. And so that compare with same region S3, Alacio can provide twice the throughput compared to the same region S3, and it really depends on how far away is your training job with your storage system. For example, if your storage system, if a remote S3 bucket or your storage system is really far away on prone storage system in another region, it may provide much more benefits compared to this. And this is actually one of the worst scenario that we can compare with. Compare with caching using Alacio, we have the same region S3. And another thing we've found that is pretty interestingly is that when Ray object store is under memory pressure, the performance gap widened the throughput of Alacio with 5 times that of S3 in these scenarios. So Alacio can help catching the data set for the Ray framework. Ray did really good job of managing the Ray task data, but it doesn't deal with the repeated data access issue. So when you use Ray to do the training job, it will still repeatedly fetch the data set from remote storage. And when you're using Alacio to utilize the unused disk resources for the caching capability, it do improve the data loading performance. And this is another one that is more focusing on the serving workloads. This is one of the screenshots that our users shared to us, so that they use Alacio to achieve 10x acceleration in model deployment. So on the left side, you can see the bars. That's the bars is that when they didn't use Alacio, how long time do they need actually to deploy their models. And the middle is like when they first deploy Alacio, how much time they actually need to deploy models. And we can see that deploying Alacio immediately like achieve only 1/3 of the time that needed to deploy their models. And on the right side, we do some co-optimization with them, and immediately that we can reduce the model deployment time to only 1/10 of the original time by removing the unneeded RPC costs and doing some like data asset optimization. That's we can achieve that performance. Okay, so we will move back to the technical part again. So it talks about how we actually integrate with the compute framework, because there are many of the storage system, but how can those storage system integrate with the compute framework? Is it through some of the storage specific APIs, or is through some other APIs? What's the connection way is better to achieve the best performance for compute frameworks? So this along with the whole Alacio technology journey. So in the beginning, Alacio is an open source started from UC Berkeley MI in 2014. And at that time, we focusing on the big data and analytics frameworks like Spark, Presto, and etc. For those framework in the Hadoop ecosystem, the key API is the Hadoop API. So Hadoop API is the first citizen API for the storage system in the Hadoop ecosystem. And later on, we moved to cloud adoption, moved to multi-cloud, cross-region, and a little bit of AI. And that's the time that Postgres API really shines, because the users, they just want to use Alacio as a local folder. They don't want to make any changes to their workload, their scripts, and etc. So that have a huge need for the Postgres API. And recently, when the whole AI shines and the whole, basically all the compute frameworks, like especially the AI frameworks, they are built around Python. Then Python API become the first citizen API in this whole scenario. And compared to Postgres API, which is highly, I would say highly uncontrollable. So Postgres API is developed basically around the kernel cores and is not designed for AI. Then it have a lot of behavior that is not targeted for high concurrent like data access. If you have like high concurrent data access, they will launch their own thread to deal with requests. They are double the CPU requirement for those requests, and also like they have like a lot of unneeded RPC costs. For example, when you are reading a file, it will have random number of get file status costs, and each get file status cost may ruin your performance. And so that when we move to the AI, first is that like the whole ecosystem is built around AI. And also like the Python API is much more controllable from a developer perspective and from performance perspective compared to Postgres API. So that's the direction that we are going. So one of the main thing that we see many of compute framework, they share the same is that the compute framework, basically many of them are moving towards PyArrow project. So PyArrow project did a really great job in the format translation. So you can read data from whatever like format to arrow format. And if you need another format, you just transfer the arrow format to that format. And it also helps you to predict your data set. Basically, whatever format that you are using in your compute framework, you can return it back to arrow or you turn it back to the format that you like Parquet format, and then persist it in the storage system. And PyArrow do a really good job in the kind of the format translation, but it dedicate the storage interface, the storage connection part to another open source project called File System Spec. I love that project. It did a really good job. It basically using that project, you can be able to access all the storage system that you want. Like from the public cloud storage to all the open, even to some private storage system that provided by Databricks or Snowflake. So everything that all the famous like storage system that you can think of, they implement the file system spec, and it basically turned that storage system API to a uniform Python IO-like interface that can easily be consumed by all the application, including but not limited to PyArrow. There are many cases they just don't need PyArrow. They just want to lower data set or lower model from random storage system, that they directly use file system spec to do that data fetching accessing. And Elasio in this picture acts as a super caching layer for file system spec. Basically, like when file system spec, they will fetch the data from the remote storage system into Elasio and then cache it in Elasio. And when they have served some read requests, they basically first come to Elasio to say that, hey, do you have the data that I want? If you have, that's great. It's much closer, it's much easier. I just directly get it and to my users. But if you don't have it, I go to the storage system to fetch it for you and then put a copy in this super caching layer. And so that together, I can even have more insights about like how much data I actually read from the storage system, how much data is actually served by the caching system, and what's the hottest data. Basically, they also add some like data visibility into what data you actually use and how much of the data is actually the hot data set in all the compute workloads. And note that like all the framework, they can share the caching layer instead of like for the file system built-in cache functionality is per node level. Basically, it's per framework, per node level. You cannot reuse it across different nodes. You cannot use it across different frameworks. But adding a super caching layer, those things can be reused. And this is a pretty simple example of like how you can access like S3 storage just like a Python IO local file system. You can do the elasio.ls, elasio.open, and read. But it's pretty similar to what you use the Python IO library. And when you integrate with some of the compute frameworks like Ray in this case, originally the line is the ray.data.read image, and you get in the S3 URL. And now you just need to pass in file system into Elasio to add that super caching layer. I think that's it for the whole talk. And feel free to use your question in the chat. I think I can't running out of time, like only 1 minute left if anybody have any question.